now let us talk about a multiplication theorem. So just now, what did we learn? That probability of any event, given that another event has occurred, we write this down as PA intersection B upon PB. Now, how can I write down PA intersection B here? It can be written down as PB into probability of A given that B has occurred. So this is our multiplication theorem. Now you must be thinking there is nothing new that we are learning here, but again it is the same thing. However, we just apply it for two types of events. Now we are going to be applying it for three types of events. Now let's say if we have to find out probability of A intersection B intersection C. So what is it going to be? P of A this would become into P of B given A has occurred, and probability of C given that A intersection B has occurred. So this way this cycle will continue. Now if we have, let's say, 4 events occurring, so again the same thing will be happening, and then in the end term we would have PD upon A intersection B intersection C. So similarly this type of pattern continues. So this is nothing but our multiplication theorem. Again, there is nothing much to understand here. You simply must remember this formula so that in future if questions are asked based on this, you would be able to solve it. Now let us talk about independent events. What are independent events? Independent events means that the occurrence of one event does not affect the other event. That means we can say that PA intersection B is equal to PA into PB. Now this is an important thing that you must remember. Now this occurs only when we have independent events. If the events are not independent, that means P intersection B would not be equal to PA into PB. So keep this thing in mind. Now what important thing that we must understand about intersection is that we know that PA intersection B is equal to PA into PB. That means for P A given that B has occurred, we used to write this formula PA intersection B upon PB. Now A intersection B, since this is an independent event, so PA intersection B can be written as PA into PB upon PB. PB gets cancelled, so we have this equal to PA. That means PA given that B has occurred is equal to PA. That means we understand that whatever be the occurrence of B, it does not affect A. That is why these two events we consider them to be independent events. Now what does this signify? This means that, let's say, if A and B are independent events, then what else can we say? That A dash and B dash are also going to be independent. A dash and B are also going to be independent. A and B dash are also going to be independent. That means this works for all types of different types of A and B combinations, whether it is complement of them, whether one of them is complement or the other one is not. So similarly, now again, if I was to take, let's say, if P A dash intersection B dash, so this would become P A dash into P B dash. Now this happens only when, again, our events are independent. If our events are not independent, then this type of equation would not be formed. Let us look at a question to understand independent events better. Two players A and B alternatively keep rolling a fair dice. So A and B are rolling a dice. The person to get 6 first wins the game. So let us say that, let us say that probability of winning the game is 1 by 6, because the one who gets only 6 will win the game. And what would be the probability of losing? That would be 5 by 6. Given that player A starts the game, then the probability that A wins the game. So we have to find out the probability that A wins the game. So A has started the game. So what can be the cases? Now I hope you all remember, even during sets and relations we had studied this. Let's say if we are talking about OR anywhere, that time we use union, and that time we use multiplication. That time we use addition sign. And whenever we are talking about intersection, we talk about and we say it is going to be multiplication. So that means multiplication is proportional to intersection, and these are proportional to AND. If these terms are there, that means you have to multiply. If let's say OR is there, that time you have to add, and we have to find out the union. So this is an important thing you must remember. I'm writing it down in here in this question because here now you will understand this concept more. Let's say if A rolls the die first and A wins it, and A gets a 6. So A has won the game. So either this can be our probability, or what can be the other scenario? If we are using OR, we use ADD. Or if A loses the first chance, B also must lose the second chance, because of course B cannot win the game. We are finding the probability of A winning. Now A is playing the game. Now A wins the game. Or what can happen is A loses the game, B also loses the game, again A loses the game, again B loses the game, and then A wins the game. So similarly this will continue up till infinity. So this is how we can find out the probability of A winning the game. So what is this? Let me substitute the values. This becomes 1 by 6 plus 1 by 6 times of 5 by 6 whole square plus 1 by 6 times of 5 by 6 whole to the power 4 up till infinity. So this is nothing but a GP. And how do whenever we have to find the sum of a GP, we write A, our first term, which is 1 by 6 here, and our common ratio. Common ratio is what here? Common ratio is 5 by 6 whole square. And now we know that our common ratio is less than 1. So our sum, what does it become? Our sum basically becomes A by 1 minus R. So simply we can write it down as A becomes 1 by 6 and 1 minus 5 by 6 whole square. And what will we get upon solving this? This would become 36 minus 25. So this becomes 6 by 11. And this is our answer. So 6 by 11 is the probability of A winning the game. Now I hope you all must have understood this. I'm going to repeat the question once again for you to understand it better. They have told us that the person who gets a 6 will win the game. So what is the probability of anyone, be it B or be it A, winning the game? It is 1 by 6, because only one number can let them win the game. So winning is 1 by 6. And so probability of losing becomes 5 by 6. Now they have told us that A starts the game, and we have to find out the probability that A only must win the game. So what are the chances that can occur? Either in the first chance only A wins the game, or first chance A loses, second chance B loses, and then in the third chance A wins, or in the fifth chance A wins, or in the seventh chance A wins. Of course, we cannot count here as B winning here, because B cannot win the game, because we have to find out the probability of A winning the game. So that is why we did here was, since all these are different cases and either of them can occur, so we are saying that either this occurs or this occurs or this occurs. That is why we add all these probabilities. Like I told here, we add whenever we are using or union, and we multiply whenever we are using intersection or AND. So here you can see that we are multiplying. We are saying that first chance A should lose, and B should also lose the second chance, and the third chance A should win. So that is why when 3 ANDs are coming, so we are multiplying this thing. So, and again, this can go up till infinity, and this basically forms a GP. We identify our GP, we solve it, and we get our answer. So this is how these type of questions are solved. Now we will be looking into the most important topics of this chapter, which is our total probability theorem and our Bayes theorem.